All right, so are you ready to dive into some serious science today?
Always.
Okay, good, because we're going to be talking about manipulating the handedness of crystals using light.
Sounds pretty complicated.
Well, it is some pretty fascinating stuff, I think. And, we found this article in Science titled The Terahertz Twist, Revolutionizing Crystal Chirality with Light.
I read that one too,
Yeah.
and it really does seem like it could revolutionize a lot of different fields. Like we could see ultra-fast memory devices or advanced optoelectronics.
That's right, and those are some big claims. But I think before we jump ahead, can you just back up for a second and just explain chirality to us?
Sure.
What does it actually mean for a crystal to be, left-handed or right-handed?
So it's kind of like your hands, right?
Yeah.
They're mirror images of each other,
Okay.
but you can't like superimpose them on each other, so
Right.
that's chirality.
Okay.
Like a molecule or a crystal can exist in two forms,
Got it.
each a mirror image of the other, but not identical.
So it's not just a visual difference then?
No.
This handedness actually affects how these crystals behave.
Exactly. So like chirality impacts how crystals interact with light and electricity.
Okay, I see.
And that's why it's so important for material science and pharmaceuticals.
Okay, so that makes sense. And so now that we kind of got the basics down, what's so mind-blowing is that this research shows that they can actually induce chirality using terahertz light.
Yeah.
I think most people probably haven't even heard of terahertz light. So
Well,
what is it?
It's basically a type of light that has a frequency between infrared and microwave radiation.
Mm-hmm.
And what makes it so special is that it can interact with the vibrations of atoms within a material,
Okay.
specifically like the crystal lattice.
So they're basically like tweaking the structure of the crystal with this light to make it chiral.
Exactly.
And they use boron phosphate in this research, right?
Yes.
And that's a crystal that isn't normally chiral, right?
Yeah, that's right.
So what exactly did they do?
Well, the way they did it is called nonlinear phononics, which
Wow.
sounds really complicated.
Yeah, it does.
But imagine hitting a bell
Okay.
at a specific point with a specific force.
Yeah.
It'll make a certain sound, right?
Yeah.
So in this case, the bell is the crystal lattice,
Uh-huh.
and the terahertz light is like the hammer.
Okay.
And by hitting the crystal with this light, they excite these very specific vibrations in the lattice.
Okay.
And it's these vibrations that actually twist the structure into a chiral form.
So they're tuning the chirality with light.
Yeah.
That's amazing.
It's pretty cool. And they were able to control it really precisely, too.
Right.
Just by rotating the polarization of the light by 90 degrees. They could actually switch the crystal between left and right-handed chirality.
And they can switch between these states really quickly, too, right?
Oh, yeah. Extremely fast.
It's like the article said picoseconds.
Yeah.
But what does that even mean? Like, how fast are we talking?
We're talking trillionths of a second.
Wow.
So, like, to put that in perspective, like, think about computers.
Okay.
They operate on the nanosecond scale. Right.
Which is like 1,000 times slower.
So we're talking about data transfer speeds that are thousands of times faster than what our phones can even do now.
Right. Imagine downloading a movie, and it wouldn't even take seconds. It would be like milliseconds.
That's a game changer.
It is.
Yeah.
It really is amazing when you think about it, like switching a fundamental property of matter at those speeds.
Yeah, and that speed could have huge implications for technology.
Absolutely.
Especially in fields like data storage and processing.
Totally. So, like, imagine storing data
Yeah.
in the chirality of crystals and being able to, like, flip between states trillions of times per second.
So it's not just like faster downloads then.
No.
This is like a completely different way to build computers.
Exactly. And it goes beyond speed, too.
Really?
This kind of control over chirality.
Yeah.
It could mean big advancements in optoelectronics, too.
Optoelectronics.
Yeah.
That field already impacts our lives in a big way, right?
It does.
I mean, lasers, LEDs, fiber optics.
Exact.
So much stuff uses that technology. Now imagine optoelectronic devices where the functionality, like the way light is emitted or absorbed, is tied to this ultra-fast chirality switching.
Okay, so like what would that look like in an actual device, though?
Let's say optical switches.
Okay.
Those are a big part of telecommunications and data centers.
Right.
Right now, they use mechanical or electronic processes, which limits how fast they can be.
Yeah.
But imagine an optical switch where the chirality of a crystal determines if light can pass through.
And we can flip that chirality so fast.
Right. Yeah.
So the switch would operate at like terahertz speeds.
Exactly. We're talking data transmission rates thousands of times faster
Wow.
than we have now.
It's really hard to even imagine that.
It is. Yeah, it kind of sounds like sci-fi.
It does.
But this is like the beginning of a whole new frontier of material science.
I mean, are we getting ahead of ourselves here, though?
Yeah.
What are the challenges to actually turning this research into real technology?
Yeah. So like one of the challenges is making the chirality last longer. Right now, it only lasts for picoseconds.
Right.
But for a lot of applications, we'd need it to last a lot longer.
So basically making the chirality stick.
Yeah. And that's going to take more research to figure out how to stabilize that chiral state.
Yeah.
And there's also the problem of scale.
Okay.
Right now, these experiments are all done on tiny crystals in a lab.
Right.
Figuring out how to make these materials on a larger scale
Yeah.
is going to be a huge challenge.
It sounds like there's a lot of work to be done,
There is.
but the potential payoff is huge.
It is.
So we've talked about how this could revolutionize computing and telecommunications.
Right?
But what other fields could be impacted by this research?
Oh, tons. Like, think about medicine.
Okay.
Imagine using light to create chiral molecules, like whenever you need them.
Yeah.
And you could control their structure and properties really precisely.
So instead of like searching for these molecules in nature,
Yeah.
or making them with all these complex chemical processes,
Right.
we could just manufacture them with light.
Exactly. And because chirality is so important in biology,
Yeah.
this could be huge. Like, it could lead to new drugs and therapies.
Right.
And it could even change how we think about tissue engineering and regenerative medicine.
Yeah. I mean, it's hard to even grasp how big of an impact this could have.
I know, right?
It feels like this one discovery could change like everything.
It really shows how connected all these different scientific disciplines are.
Yeah.
Like, a breakthrough in physics can lead to new materials.
Yeah.
And then those new materials can change medicine and engineering.
It's amazing.
Totally.
We started talking about manipulating crystals with light.
Right?
And now we're talking about making new drugs and growing organs.
I know, it's crazy.
It's incredible.
Yeah, that's what makes science so cool.
Yeah.
It's all about discovery and exploration and making connections.
And that's what makes this exciting for you listening to this right now.
Yeah.
This research might seem abstract,
Yeah.
but it really could shape the future in big ways.
That-
The technologies that come out of this could change how we communicate,
Uh-huh.
how we treat diseases.
It really is a reminder that science is constantly pushing the boundaries.
Yeah.
And by staying curious, you can be part of that.
So as we wrap up this deep dive, I want to leave you with one last thought.
Okay.
If we can control chirality with light, what other properties of matter might we be able to manipulate in the future?
That's a good question.
What new materials, what new technologies, what new possibilities are out there?
It's exciting to think about.
It is. Keep those questions in mind, keep exploring, and join us next time as we keep diving into the world of scientific discovery.